Hello and hi everyone. Here is Chapter 3 Part 2 Angle Modulation with Madam Hafiza. Okay, before that, let's recap back the Part 1 Chapter 3. So here given the carrier swing CS is equal to 2 delta F and the unit is in Hertz, and meanwhile the frequency deviation delta F equals to KF/Vm. The unit is Hertz, and given the deviation sensitivity Kf equal to delta omega over delta Vm, where omega is radian per second and Vm is volt, and also it can be written as Kf equal to delta F over delta Vm, and the unit is Hertz over volt. And here is the modulation index. M equals to delta F over Fm, and it is unitless. Okay guys, remember the sideband as AM. For the sideband of AM, we have here the FC, which is the carrier frequency, and here we have F lower sideband and F upper sideband. Here is the frequency spectrum of the AM. Okay. For the FM, is a product of any modulation. So angle modulation FM and PM produce more bandwidth compared to amplitude modulation because of it has multiple of sidebands. Alright, bandwidth of an FM signal is usually wider than that of an FM signal with the same modulating signal. So for FM, infinite number of pairs of upper and lower sideband will be generated, and this is the different features of angle modulation. Lastly, more sidebands means more immune to noise. So sidebands and the modulation index. Here is the relationship between sidebands and the modulation index. FM produces pairs of sideband space from the carrier in multiples of the modulating frequency. The number of significant pairs of sidebands determined by modulation index. And the modulation index is in the FM signal is the ratio of the frequency deviation delta F to the modulating frequency Fn, and M equals to, which is M equals to delta F over Fm. So significant sideband. Here is the example of sidebands. Here we have, in the middle we have the frequency carrier and its amplitude. On your right side is your upper sidebands, and on your left side is your lower sideband. So it is a pair of 1, 2, 3 sidebands, and given the bandwidth spectrum is 6 FM. So 1, 2, 3, 4, 5, 6. 6 FM. Another example of 16 FM, which is the bandwidth of the spectrum. So here is the FC, the middle of spectrum, and the rest is the sidebands. Here we have 8 pairs of sidebands. Here is the lower sideband, and here is the upper sideband. So next is the FM equation. When a modulating signal is a single sine wave, the FM equation is Vfmt is equal to Vc cos in bracket omega ct plus m sine omega mt. Or it can be written in this form. Fm in bracket t is equal to Vc sine omega ct plus m sine omega mt. Here is your voltage, your amplitude of carrier. Here is the omega carrier, and here is the modulating index, and here is the omega of modulating frequency. To expand the equation into complete FM equation, including each sideband, it is difficult. But Bessel function is used to solve the equation. So next I will show you the. So let's take example of this FM. FM is equal to Vc cos omega ct m sine omega mt. By using the trigonometric identities, given the cos A plus B equals to cos A cos B minus sin A sin B. So first of all, we need to partition the first equation. Alright, here is A and here is B. Hence, write down the full equation. VFMT Vc cos A omega t cos B m sin omega t minus Vc sin omega ct sin m sin omega mt. Here the B. So where cos m sin omega mt and sin m omega mt is a trigonometric series called a Bessel function. And then next we will expand this equation into the Fourier series here. Cos m sin omega mt, here is the equation, sin m sin omega mt, and here is the equation for even and odd. Next, we substitute the equation into this full FM. So we have here, and then next here, the even and the and odd, and then expand using the Bessel identity here and here. Next, it will expand into this partition of equation. So we have here the carrier band, the sideband 1, the sideband 2, the sideband 3, the sideband 4, and the end sideband. So here is the carrier band, because here is the amplitude of carrier times with the Bessel product. Next is the first sideband, VCJ1M in bracket omega C plus omega M. This is the first sideband, upper sideband. So the first upper sideband, and here is the first lower sideband, because of here is the plus and here is the minus. Next is the second sideband, same like the first one, and here is plus omega C plus 2 omega mt, and here is omega C minus 2 omega mt. So here is the second sideband. And then next is the third sideband, and so on. So where M is the modulation index, Vc is the peak amplitude of the unmodulated carrier, together with the J node, with the carrier component, J1M with the first set of side frequency displayed from the carrier by omega m, J2M the second set of side frequency displayed from the carrier by 2 omega m, and Jn is the nth set of side frequency displayed from the carrier n. So here the number we will get from Bessel function of the first kind. Here is the curve or the graph of the Bessel function. And then, okay, to make it easier, you can refer to this table. So on your left is the modulation index here. And then follow with the carrier, the component of carrier, and the rest is the sidebands. As I mentioned, the modulation index will show how many sidebands for your FM. For example, if your modulation index is 0.5, so your sidebands will be 2. So the significant sidebands are those that have amplitude greater than 1% in the Bessel table. So it shows that J0 squared plus 2J01 plus 2J2 squared plus 2J3 squared plus so on until 2Jn squared is equal to 1. So here is the example. So given m equals to 1.0, okay, so look at the sideband here. So we have 1, 2, 3 pairs of sidebands, and the carrier component will be 0.77, and the first is 0.44, second 0.11, and the third or the last is 0.02. So here is how we'll generate the frequency spectrum. So we have the y-axis in amplitude and the x-axis in frequency. Because of it has 3 sidebands, so here we have upper sideband, 3 upper sidebands, and 3 lower sideband. And the frequency for the first sideband is Fc plus Fm. Next, Fc plus 2 Fm. Next, Fc plus 3 Fm. This is for the upper. Meanwhile, for the lower, first lower sideband Fc minus Fm. Second lower sideband Fc minus 2 Fm. And third sideband, lower sideband Fc minus 3 Fm. For the amplitude, we follow this equation. For the middle one is the carrier is Vc times J0. So any value of unmodulated carrier amplitude will times with the component. And this spectrum will be symmetry. So here is another example. M equals to 2. And the sideband will be 4. So here is the spectrum frequency for M equals to 2. So we have Vc, the amplitude of the carrier, Fc, the frequency of carrier signal, and Fm is frequency of modulating signal. So here is the combination of the amplitude. And this is the complete set of the amplitude and frequency of M equals to 2.0. So here we have the upper sideband frequency and the lower sideband frequency and here is the carrier frequency. Here is the amplitude of the upper sideband, and here is the amplitude of the lower sideband. And in the middle is the carrier amplitude. So example 1, the modulation index M equals to 1. So draw the amplitude spectrum of frequency domain if Vc is equals to 50 volt. So here we take it from the vessel table. Thus, the amplitudes are VCJ0 for the carrier, VCJ1 for the first amplitude, VCJ2 for the second amplitude, and VCJ3 for the third amplitude. And here is the amplitude spectrum of M equals to 1. So, end of part 2. Stay tuned and thank you.